All right, so I'm going to begin this video by defining this object called an ordered set. We will make the connection to rationals a bit later, but at this point I'm going to define this in abstract terms because this is something that is applicable and usable even beyond the specific context that we are discussing. So what is an ordered set? Let's begin with a definition. So let S be some set. Okay, now what does it mean to have an order on the set? An order on the set is a relation. I'll explain what that is. It is denoted typically by the less than symbol. With the following property. First, if you have, let's say, x and y that belong to the set, then one and exactly one of the following hold. So either you can have x itself equal to y, or you would have x, well, less than y. I'm using less than because that's what we kind of use this symbol typically for, but remember this set need not be a set of numbers, right? So this is simply a relation between elements of the set, or you have y less than x. So what does this mean? A relation is essentially, you can think of it as a function that takes two arguments of the set, right, and pops out a binary answer, either true or false. True meaning that the relation holds, and false meaning that the relation doesn't hold, right? So when I say x less than y, it means that, well, under the relation that you have defined, when you pass the arguments x comma y in that order, it gives you true, right? Similarly, if you give y comma x to the same argument, it gives you true, right? That is what this means. So a relation is basically, you can think of it as a function with two arguments taking either values true or false. So when we say x less than y, we mean that when you pass it the arguments x comma y, it is true, or alternatively it asserts that as per your definition of the order, x is less than y. Again, I emphasize that x and y don't have to be numbers. The set S can be any abstract set. I'll give a couple of examples going forward. But between any two elements x and y, if they are not equal, the first requirement here says that either x should be less than y or y should be less than x under the order that one has defined. Okay? This is the first condition that an order should satisfy. The next condition is the following. So if you have, let's say, x, y and z belonging to x, and if it turns out that x is less than y and y is less than z, then you must have x less than z. Okay, so the order that you have defined, see, order is a pairwise relation, right? So it is a relation that holds between any two elements of the set, but there should be a certain transitivity in the definition of the order. Namely, transitivity, yes. Namely, if x is less than y and y is less than z, then your order should be such that x should also be less than z, right? So this is, of course, the natural, the natural property that you would expect if order is defined in the conventional manner when it comes to numbers. But in general, in the abstract definition of an ordered set, we impose this condition of transitivity in order for the order to be a valid one. Okay, so this is the definition of an ordered set. Let me now give you a couple of things to keep in mind. Firstly, we read, I've already been doing this, but I read this assertion as x is less than y. right? I use this because we are used to, well, using the symbol to mean less than. So x is less than y is just an English way of saying this. Okay, but x and y need not be numbers. They are just elements of this abstract set on which you have defined the order. So whenever this holds, we will say x is less than y. Okay. Sometimes if I want to say, sometimes we also write x less than y as, okay, we sometimes also write not and, as. We sometimes will write x less than y as y greater than x. Okay, this is just these are two equivalent things. This means this. All right. And the third thing is that whenever we write x less than equal to y, this means that either x is less than y as per the order, or x is equal to y. Okay, so for any abstract ordered set, it is possible to write x less than y, y greater than x less than equal to y, similarly x greater than equal to y, and all of these would mean the natural thing with respect to the order, right? And specifically for your order to be valid, you need these two properties. For any elements of the set that you pick, either they are equal, of course, you pick the same element, or one should be less than the other, or the other way around. So therefore there has to be an order between any two elements of the set, right? And it should satisfy the transitivity property, that if you have x, y, z in the set, if x is less than y, y is less than z, then x should be less than z. Okay, so this is what we formally mean by an ordered set. Let's give a couple of examples. The first example is, of course, natural. The set of rationals that we have been talking about so far. So this is an ordered set, with the order meaning the standard thing, right? In this case, I will say that x is less than y if y minus x is positive, right? So the standard ordering over the rational numbers gives you an ordered set. All right. Actually, I haven't mentioned this explicitly. Maybe I'll just do that here. So by definition, an ordered set is a set with an order defined on it. Yeah, I needed to clarify this because in this definition, we only define what it means for something to be a valid order on the set. So once you have a valid order on the set, the combination of the set and the order together is called an ordered set, right? So to define an ordered set, you need to have a set, and you need to define a valid order on the set. So now let me give another example which is not numerically related, and this would be let's say between words of the English language, or any language for that matter. Right, with the lexicographic order. Yes, if you haven't heard what lexicographic is before, lexicographic order is simply the order in which the words show up in the dictionary, right? So A through Z, you look at the first, so to know whether one word comes before another in the dictionary, you look at the first letter and you say whether it shows up before the other in the order from A to Z. If there's a tie there, you move on to the next letter and so on, right? We've all used a dictionary before. There is an ordering of words in the English language based on, so a word x is less than the word the word y, if x shows up before y in a dictionary, right? So that is what we mean by a lexicographic order. So again, so therefore these are not numbers, but nonetheless it's an ordered set, because it's a set, the set of all words in the English language, and the order is determined by, well, if x is less than y, if x shows up before y in the dictionary. All right, so these are a couple of examples of ordered sets. Now that I have defined ordered sets, next I need to define this notion of upper and lower bound on an ordered set. Okay, so I'm going to do these upper and lower bound definitions in parallel. Suppose you have an ordered set. And suppose you have some subset E of S. Okay, now I'm going to define what it means for the set E to be bounded from above. Suppose there exists an element, let's call it beta, in S such that x is less than equal to beta for all x in E. Okay, so what have we said? We have an ordered set. We have a subset E of S. I'm saying suppose there exists an element beta in the set, in the mother set S, such that for every x in E, beta is in fact greater than or equal to x. Right? If this is true, we say that the set E is bounded from above. Right? And we say that beta is an upper bound of E. Right? So this is simply saying that if you have an ordered set and if you can come up with some element such that for this that element is greater than or equal to every element of a set E, we say that the set E is bounded from above, and the element beta which is greater than or equal to every element of E is called an upper bound of E. Right? Now again, as I said, S need not be a set of numbers, and so this is something that can be defined for any ordered set. Okay, for any ordered set, it is meaningful to say that such and such subset of the ordered set is bounded from above, and that this element is an upper bound on this subset, right? It is meaningful to say this in the generality of an ordered set. Okay, so I'm going to go one step further and define now what is called the least upper bound. So again, S is an ordered set, E is a subset of S. If so, I won't write the S being an ordered set bit. Say E is a subset of S, which is an ordered set. Okay. Now, if and E is bounded from above. Okay. Now, suppose there exists an element alpha that satisfies this property. If there exists alpha belonging to S such that two things are true. One, alpha is an upper bound on E. Okay. And if another number gamma is less than alpha, then gamma is not an upper bound. Okay, so what are these two properties? So E is a subset of S which is bounded from above. What does it mean to say that E is bounded from above? That there exists an upper bound on E, right? Now suppose I can find an element alpha that satisfies the two properties that I've written. One, that alpha is an upper bound on E, and the second property is that any number that is less than alpha is not an upper bound of E. Okay? If these two properties are true, we say that alpha is the least upper bound. Least upper bound short LUB or supremo. right? And specifically we will usually write that alpha is sup of E, right? So what is the supremum or least upper bound of a set of a subset E that is bounded from above? The least upper bound, if it exists, of course, is a valid upper bound on the set of this on the set E with the property that no other element which is less than that number alpha is an upper bound. So in that sense, it is the least upper bound. And again, if such a thing exists, it is also called the supremum, and we say alpha is equal to sup E. Okay, some of you have probably already encountered the sup notation in the context of real numbers, but this is just a more general definition of the sup in the context of an abstract ordered set, right? So everything that we have done with respect to upper bounds can also be said with respect to lower bounds. So similarly, I can define what it means for a set to be bounded from below, right? So let S be an ordered set and E be some subset of S. If there exists, let's say, some beta belonging to S that satisfies the property that beta is greater than or equal to beta is less than or equal to X for all X in E, then we say that E is bounded from below and that beta is a lower bound on E. Right? So this is the natural definition. What does it mean to say that a subset E of the ordered set is lower bounded? If there is an element such that it is less than or equal to every element of the set E. Right? In that case, E is bounded from below and beta is in fact a lower bound on E. Right? Similarly, there is the definition of a greatest lower bound. Remember, earlier we talked about the least upper bound or supremum. That was meaningful for a set that was bounded from above. If there is a set bounded from above, it is meaningful to define. It's not guaranteed, there's no guarantee of existence, but it is meaningful to define what it means for an element to be the least upper bound, right? For a set that was bounded from above. Similarly, for a set that is bounded from below, it is meaningful to talk about what is the greatest lower bound. Okay, so the shall we say the definition is going to be analogous. So again, E is a subset of S. S is an ordered set. And E is bounded from below. Now, if there exists alpha in S such that on one hand alpha is a valid lower bound, and any gamma which is greater than alpha is not a lower bound. Right? So on one hand, this alpha is a lower bound, and anything more than alpha is not a lower bound. Right? In that case, we say that alpha is the greatest lower bound. Right? That is sometimes abbreviated as GLB or infimum. Infimum of E. Right? And sometimes this is written as inf of E. Okay? So if you have an ordered set, moral of this slide, if you will, is that for any subset of the ordered set, it is meaningful to ask whether the subset is bounded from above or bounded from below. Similarly, it is meaningful to say that this element is an upper bound on this subset E, similarly this element is a lower bound on this of this subset E. And once you have an upper bound, it is meaningful to ask, or at least it is meaningful to define a least upper bound. I emphasize once again that I have not yet said that a least upper bound must exist. In fact, that is something that I'm going to address next. But if it exists, it's meaningful to assert that what it means for this element to be the least upper bound or greatest lower bound, right? If for alpha to be the least upper bound of a set E, it has to be an upper bound, and nothing less than alpha should be an upper bound. Similarly, if alpha is to be the greatest lower bound on a set E, it has to be a lower bound, and nothing more than alpha should be a lower bound, right? That intuitively makes sense. Least upper bound is also called supremum, greatest lower bound is called infimum, right? And again, many of you would have probably encountered sup and inf in the context of real numbers. All we have done is defined it in the generality of an abstract ordered set. Okay, so next let me get to the property that I have been building to with all this notation. And that is, what does it mean for an ordered set to have the least upper bound property? An ordered set, again S. When I say ordered set S, of course I mean not just S, but I need the tuple consisting of S and the order, a valid order that has been defined on S. Okay, an ordered set S has the least upper bound property if for all E will subset of S that is upper bounded, sup E exists. Okay, so what this property tells you is that an ordered set satisfies what we call the least upper bound property if for every subset of S that is bounded from above, a least upper bound or supremum exists. Remember, in the earlier definition, we only defined what it means for something to be the least upper bound. We didn't know about existence. If you are guaranteed that every subset of E that is bounded from above has a supremum, we say that the ordered set satisfies the least upper bound property. Okay. Similarly, we say that an ordered set satisfies the greatest lower bound property if the same is true. An ordered set S has the, well, I'll just try this in for short, the greatest lower bound property if for all E, which is a subset of S that is lower bounded, inf E exists. Right? So if the subset E itself is not lower bounded, it doesn't make sense to talk about an infimum, right? And or a greatest lower bound. You look for a set, an ordered set S satisfies the greatest lower bound property if for every subset that is lower bounded to begin with, which means it has a lower bound, there should also be a greatest lower bound. Right? So whenever there exists a lower bound, there should be a greatest lower bound. Similarly, an ordered set has the LUB property if whenever a subset has an upper bound, it also has a least upper bound. Okay, so that is what these properties mean. Okay, so with all of this said, now we can go back and take an example with respect to the rationals. Now at this point, you need to be able to recall the examples that we did in the first video. Those examples in fact show that the ordered set Q, right, with the standard ordering, does not have either property. Or the GLB property. Okay, the rationals do not satisfy the LUB property, or for that matter the GLB property. How do I demonstrate this? Remember, we had defined these subsets. So let me just remind you again. So A was the subset of non-negative rationals such that the square was less than 2. B was the set of non-negative rationals such that the square is more than 2. Okay, so the first thing to note, of course, these are subsets of the rationals, right? This set here A is upper bounded. That's easy enough to see because I can demonstrate an element which is greater than or equal to every element of A. For example, I can just take the number 2, right? The number 2 is greater than the number, any number x that belongs to A, and so therefore the subset A of the rationals is a set that is bounded from above. Similarly, it's not difficult to see that the set B is lower bounded. Right? Why is this lower bounded? It's easy, right? For example, 0 is a valid lower bound on B, right? So we have just defined two subsets of Q, one that is bounded from above and the other that is bounded from below. Now, how do I demonstrate that Q? I'll just demonstrate that Q does not have the LUB property, the least upper bound property, right? How do I do this? Well, what you do is that, let's look at A. Okay, it has an upper bound. Let us ask whether the supremum exists, right? Now, what is supremum? It is the least upper bound, right? Now, question, does, sorry. Okay. So yeah, I want you to think about this for a moment before you, before I give you the answer. Based on the properties that we proved, in fact, the soup of A, in fact, does not exist. Why is that? Because while there are upper bounds on A, in fact, every element of B is in fact an upper bound on A. Right? Every element of B has been designed in such a way that it is in fact an upper bound on A. So B is in fact the set of all possible upper bounds on A. Okay? And we have already proved that B does not have a smallest element. So therefore, there is no supremum of A. Why? Because B has no smallest element. Right? Go back to the argument if this is not immediately obvious to you. Firstly, the first observation is that the set B is precisely the set of upper bounds to the set A. Okay. Now, if you give me any upper bound, in other words, if you give me any element of B, I can give you another element that is smaller than that element. That was part of the construction that we did in the previous proof. Right? So therefore, it does not have a least upper bound, because if you give me any candidate upper bound on A, I can give you another number which is also an upper bound but smaller, which means that therefore the supremum of A or the least upper bound of A does not exist. Similarly, you can argue that inf of B does not exist. Okay, why does the inf not exist? Well, B is of course lower bounded, so I'm allowed to ask whether an inf exists or not. In fact, the set A is precisely the set of lower bounds to B, but we have proved that A does not have a largest element. In other words, even though A is composed of all lower bounds of B, there is no such thing as a greatest lower bound or infimum, because if you give me any lower bound, by construction from the previous proof, I can give you another lower bound which is larger, right? And so therefore there is no such thing as a greatest lower bound. Okay, so the moral of the story in all of this is that the set of rationals defined as an ordered set with the standard ordering that we define over the numbers does not have the least upper bound property or the greatest lower bound property. In other words, you can have bounded sets, bounded subsets of the rationals such that even though there is an upper bound, there is no least upper bound. Even though there is a lower bound, there is no greatest lower bound. Okay, so that is the main thing that I wanted to define. And in fact, when we define the reals, which you can think of as basically like extending the set of the rationals, we will in fact define the reals in such a way that it satisfies these two properties, the greatest lower bound property and the least upper bound property, right? So one of the shall we say the construction principles of the real line is to precisely solve this problem. That is, I want to extend the rationals in such a way that that extension in fact satisfies the greatest lower bound property or the least upper bound property and the least upper bound property. Now, why did I say or? Well, it turns out that it's in fact the same thing for a set to satisfy the least upper bound property as it is to satisfy the greatest lower bound property. Okay, so even though I have defined these as two separate properties, essentially it's the same. An ordered set has one property if it satisfies the other. Okay, so before we talk about the reals, let me just prove this statement to you. This is actually our only rigorous proof in this video. So the statement I'm trying to make is the following: let S be an ordered set okay, S satisfying the LUB property What is the LUB property? The LUB property is whenever there is an upper bound, there is a least upper bound. This is equivalent to S satisfying the GLB property. Okay, so essentially these two properties are equivalent. So if you have any ordered set that satisfies the LUB property, it turns out that for free the same ordered set also satisfies the GLB property. So establishing any one of these two properties implies the other. Okay, and so I didn't need to actually write that second argument. Once I tell you that the rationals don't satisfy the LUB property, it follows in fact that the rationals don't satisfy the GLB property as well. Okay, so now let me give a proof to this. Before I begin the proof, I should point out that when students see this, their first intuition is to rely on some sort of a subtraction or a negation. That is that, if I have a set that is bounded from above, then the minus of that set is bounded from below, and so an upper bound on the earlier set now becomes a lower bound on the minus set and stuff like that, right? That is the default approach that students are tempted to take. But I should point out that we are proving this in the generality of an ordered set. Okay, what that means is that there is no addition or subtraction property that we have defined on this set. All we have is that one ordering. Okay, so I don't know, there is no such thing as A minus B for two elements A and B of the ordered set, because that operation is not necessarily even defined. Okay, so this does require a I wouldn't say difficult, but at least slightly non-trivial proof. Okay, so the proof, as you would expect, has two parts. Right? First, I need to prove that if S satisfies the LUB property, then it satisfies the GLB property, and then of course I have to prove the other way around. So I'm only going to prove one of these, and the other will follow along similar lines, and I'll leave that as an exercise. So part one of the proof, which is this direction of the proof, which is I start off by assuming that S satisfies the LUB property. Assume S satisfies Okay, so assume that S satisfies the LUB property. I have to prove that therefore S also satisfies the GLB property. Okay, so now again, suppose that I have a subset E of S is lower bounded. Okay, what I need to prove in order to prove that S satisfies the GLB property, I need to show that for any subset E of S, which is in fact lower bounded, there should be a greatest lower bound or infimum. In other words, I need to show that inf of E exists. Okay, that is what is involved in showing this. So I'll just write that down. We have to show that inf of E exists. Okay, this is what I need to show. Now, how do I go about doing this? Okay, this is the way we do this. Let L denote the set of lower bounds now. Why is this set L non-empty? Well, because E is lower bounded. The fact that E is lower bounded means there exists a lower bound, which means that the set L of all lower bounds of E must necessarily be non-empty. So clearly L is not empty. Okay. Yeah. So moreover, every element of E is an upper bound. Okay, this is important. So if I have a subset E which is lower bounded, okay, now I can define the set of lower bounds, right? Let L be the set of lower bounds. Not only is L non-empty, but L is bounded from above. Why is L bounded from above? Well, because every element of E is in fact an upper bound on L. Okay, so think about that a little bit and convince yourself that that is the case, right? What does it mean for something to be an element of L? It means that that element is less than or equal to every element of the set. Okay, but moreover, this property is satisfied by all elements of L as well. So just write that down and convince yourself of the statement that I have written here. Namely, that if I look at the set of lower bounds of a set E which is bounded from below, the set of lower bounds is non-empty and the set of lower bounds is bounded from above. In particular, every element of E is in fact an upper bound on L. Okay, so I have assumed that S satisfies the LUB property and I have defined this set L which in fact has an upper bound. Okay, so by the LUB property, the sup of L exists. Okay, so again, I want to prove that E has an inf. In the process of proving that E has an inf, we have first defined the set of all lower bounds on E. It's trivial to verify that that set is non-empty and in fact also bounded from above. Now, because S satisfies the LUB property, the supremum of L therefore exists. I'm just calling it alpha. Okay, and my claim is that alpha is also the infimum of E. Okay, so if I'm able to prove this claim, basically the proof is done, right? Because I have demonstrated that for any set E which is bounded from below, in fact the infimum exists, right? And in fact I've given you a constructive way, quote unquote, of arriving at that infimum as well. The infimum, if this claim is true, is precisely the supremum of the set of lower bounds of the set E. Okay, so here is my claim. I need to prove that alpha, which by definition is the supremum of L, is in fact also the infimum of E. Okay, so now there are two parts to this claim. The first part of the claim, in order to prove that alpha is in fact the infimum, of E, I need to first show that alpha is actually a valid lower bound. Okay, so for something to be the greatest lower bound, it has to first be a lower bound. Okay, so this is how one goes about proving this. So again, this is something that will require some thought. So yeah, make sure that you spend some time to internalize this. My first claim is the following: if gamma is less than alpha, this implies that gamma does not belong to E. Okay, remember alpha is the supremum of L. In other words, it is the least upper bound of L. Sorry, least upper bound of L. Okay, now if I take an element gamma which is less than alpha, I claim that gamma couldn't possibly lie in E. Okay, so I want you to think about this. So this is, think. Think about this and convince yourself about why this is the case. Again, even though it is tempting to think of these elements as numbers, remember we are proving a property about ordered sets. Okay, so whatever argument you give, right, you should not, for example, use use ideas from numbers to argue your statement. Like, I take these two elements and define the average of those two elements. The average doesn't exist because at this point all we have is an ordering. So you have to just use the definition of the sup and the inf, that is all, in order to argue this. All you know at this point is that alpha is the least upper bound of L, where L is the set of lower bounds of E. So now I leave it for you to just formally argue out that if gamma is less than alpha, then gamma couldn't possibly lie in E. Okay. Now if I invert this statement, that A implies B is of course the same as negation B implies negation A. If I invert this, that means that if gamma does belong to E, then gamma is going to be greater than or equal to alpha. Okay, and what does that mean? That alpha is less than or equal to every element of E. Implies that alpha is a lower bound. Right? So this is in fact the first property that we wanted to show. In proving that alpha is the infimum of E, the first thing we needed to show is that alpha is in fact a valid lower bound. And the way we proved that is through this statement, which I'm going to leave for you to think, and then I will address in detail in the interaction session if there are doubts about this. Okay, so this is what you have to argue, that if gamma is less than alpha, that gamma does not belong to E, which implies in turn the following statement, that gamma belonging to E implies that alpha is less than or equal to gamma, so therefore alpha is a valid lower bound on E. Okay, the next statement is that if you have any beta which is greater than alpha, this implies that beta does not belong to L. In other words, any number that is more than alpha is not a lower bound. On one hand, alpha is a lower bound and nothing more than alpha is a lower bound. Okay. Now, why is this true? Well, this follows quite trivially. This is because of the fact that alpha is itself a valid upper bound on L, which means alpha is in fact greater than or equal to every element of L, right? Because it's an upper bound. So therefore, if beta is more than alpha, beta couldn't possibly be in L because alpha is an upper bound on L. So because alpha is an upper bound on L, no element of L could possibly be more than alpha, right? So if beta is greater than alpha, then beta, does not belong to L. Okay, and these two properties in fact complete the argument of the claim. Namely, the first bullet point here shows that alpha is in fact a valid lower bound on E, and the second part shows that nothing that is greater than alpha could possibly be a lower bound on E. So put all of these together and we have shown that alpha is in fact the infimum of E. Okay, so what we have done is essentially used the LUB property to show that the GLB property holds. We have used the LUB property to show that if I have any subset of S that has a valid lower bound, it also must have a greatest lower bound. Okay, and the way we went about proving this is important. Remember, I don't have any notion of addition and subtraction defined on this set. All I have is the order. So therefore the proof has to only use the order. This is very important, right? So it is very instructive to understand how the order was used and the LUB property was used to show that E in fact has an inf. Okay, so yeah, till you are, you might want to go through the proof somewhat carefully a couple of times before you actually understand every step of this proof. All right, and if you do understand every step of this proof, it should be easy enough for you to write the opposite implication. So the opposite implication, this side of the proof is exercise. Right? That will follow along similar lines. So if you have understood here how the LUB property was used to establish the GLB property, a very similar line of argument would also show the other way around. Okay, so to summarize what we have done so far, we have defined an ordered set, right? For subsets of an ordered set, it's meaningful to talk about whether the subset is upper bounded, whether the subset is lower bounded. It is meaningful to also define these two concepts called sup and inf, or the least upper bound and the greatest lower bound. Then we define this property, right? We say that this ordered set S satisfies the least upper bound property if for every subset that has an upper bound, it should also have a least upper bound. Similarly, we define the GLB property. And then we said that these two are in fact equivalent, right? For any ordered set, satisfying the LUB property is equivalent to satisfying the GLB property. Okay, so with that we'll stop here, and this will in fact act as some sort of a stepping stone towards motivating the definition for R, right? So the main takeaway of this is that we have defined these properties, the LUB property and the GLB property, but do recall that the rationals do not satisfy either property. The rationals do not satisfy the LUB property, or equivalently they do not satisfy the GLB property. All right, so with this we'll stop and continue from this point on in the next video.